Good morning to all of you.
Good morning, sir.
Good morning. So, is my screen visible?
Yes, sir, it is visible.
Okay. So, are there any questions, doubts before I proceed further? Anybody? Any question, doubt? I think it is important that whatever I teach, so after the class, you should just go through at least once and make sure that you understand all the things. And whatever doubts and questions are there, you can actually ask. You can ask before the class, you can also ask after the class. Okay, so then let me start. So last class I was talking about the approximate analytical solutions. So I had given the steps, no, the four steps. So last, so approximate analytical solution. So this is what we were discussing. So I had said that the four steps. So first step was to assume an approximate solution. Generally, that can be a polynomial, and you'll have to, of course, make sure that it is differentiable up to the highest order derivative present in the differential equation in which you are going to substitute that approximate solution. So that was one. And of course, also we look at that, no, we have whatever highest power term we have, so all the lower power terms should be included, no, in the approximate solution. Then the second step I had said that now eliminate some of the unknown constants in the assumed approximate solution by satisfying the boundary condition. And then the third step is, so now the whatever after no eliminating some of the unknown constants from the approximate solution, whatever we get, we substitute that in the differential equation, because that's an approximate solution, it will not satisfy the differential equation. So whatever balanced quantity we get, we call that as domain residual, because it is, coming from the differential equation which is valid over the entire domain. So we call it as a domain residual. And then the fourth step I had said that obtain the remaining constants by minimizing the domain residual. So how to do that, that is what we are going to discuss. So I'm going to take some examples. So let me first take one example on this. So example 1. So let us take the same problem, the this rod problem which I had said. I had derived the differential equation for this. So let us say that this is the rod subjected to a distributed load, q. Q is, let us say that q is constant throughout the length, and the product of Young's modulus and cross sectional area, that is EA, is also constant. So and the x coordinate, no, the this is the x coordinate, and in the same direction we measure the displacement. So here, as I already said, that EA and Q, they are constant along x, so they do not change along length of the rod. So now you already know the differential equation. So for this we have derived the differential equation. So I had said, no, if you recall that d by dx of EA into, in the last class we derived this differential equation, plus q equal to 0. Now if EA is constant independent of x, so that can be taken out of the derivative actually. So you can directly also write this as EA into d2u by dx square plus q equal to 0. So this is the differential equation, and the boundary condition for this problem are boundary conditions. So u equal to 0 at x equal to 0, that is one boundary condition. So no, the total length is, let us say, is the L. So the length, no, the length is L. So also we have I had discussed that du by dx for this case is 0 at x is equal to L. So these are the boundary conditions. So this is a problem. No, this particular deformation in the rod is governed by this differential equation and these two boundary conditions. So now the first step of the approximate solution, if we look at, so first step is to assume an approximate solution. So let us say we choose to assume an approximate solution in the form of a polynomial. So then whatever polynomial we assume, because we are going to substitute in this differential equation, and the highest derivative of u in this differential equation is second derivative. So we need a polynomial which is differentiable at least twice, and that means we should have terms at least up to x square. Of course we can always go for more number of terms, but minimum requirement is that we should have the quadratic terms. So if we have x square, its second derivative would be non-zero, so that means it is differentiable twice. So based on that, then we Anaja already said that in this case we are going for highest power of x as a square. So we should have before that constant term and a linear term. So we come up with a0 plus a1x plus a2x square. So x is the coordinate, of course, as you know, and the a0, a1, a2 are unknown constants. These are unknown constants. So this is the minimum, of course. No, if you want, no, for the better accuracy, you can, depending on the problem, you can go for the cubic term also. So you can have plus a3x cube plus you can have a4x power 4 and so on. So you can actually keep on doing, depending on the problem, you can, an accuracy requirement, you can increase the number of terms in this. So that's the first step. So we looked at the highest order derivative and then decided that minimum we should have quadratic term x square term, and then before that we have to have all the terms, that is constant and linear term. So finally we come up with this assumed solution. Then next step is to eliminate some of these constants by satisfying the boundary condition. So first boundary condition we said u equal to 0 at x equal to 0. So if you look at here, now this is the solution, assumed solution, and in this if you put x equal to 0, so no, this term will be 0, this term will be 0, only what you will have is a naught. So when I evaluate u at x equal to 0, I get a naught, and we know that u equal to 0 at x equal to 0, so a naught must be actually equal to 0. So that is one condition we get. The second boundary condition we have got is that du by dx equal to 0 at x is equal to L. So now in this case, now we differentiate this expression. So if you look at now here du by dx, so du by dx is going to be a1 plus 2a2x. And now in this, if we put no x is equal to L, so you will get a1 plus 2a2L, and this is equal to 0. So then what you can do from this, you can say that basically a1 is either you can express a1 in terms of a2, or you can express a2 in terms of a1. Anyone you can do actually, because no, this is only one equation and these are two constants. चरण स्पर्श मास्टर साहब, मैं अभी क्लास अभी मैं क्लास ले रहा हूँ। क्या कर रहे हैं? क्लास क्लास, हाँ। अच्छा अच्छा अच्छा, चलिए ठीक है, पहुंच गए क्लास? हाँ हाँ, ठीक ठीक है, फिर बात हो जाएगी, जनरल था। हाँ, चरण yeah, sorry for the disturbance. So yeah, now what I was saying is that you have these two constants a1 and a2 and only one equation, so you can express any one constant in terms of the other. And if there were more terms in the solution, then no, you would be able to express one constant in terms of the one or more constants, depending upon how many terms be assumed in the taken in the approximate solution. So in this case, say we can say a1 is equal to minus 2a2 into L. And now see with this, no, we look at a naught is already now 0 and a1 is minus 2a2 into L. So now if we look at after the second step, that is after eliminating some of the constants from the approximate solution, so we will have A0 is 0 in this, and A1 is minus 2A2L, so minus 2A2L into x, and of course A2 remains as it is, A2x square. So now you see that there is only one constant, that is A2 left out. I can take A2 common here, and I can write this expression as x square minus 2LX. So yeah, so finally, after eliminating some of the unknown constants from the approximate solution, in this case A0 and A1, we get this as an approximate solution. Now this approximate solution, as you see, has one unknown constant, that is A2. So now how do we get that A2? So the for that, that is the next step is we no substitute this resulting approximate solution, that is whatever we have got over here, we substitute this in the differential equation. And if you look at, this is our differential equation. In this differential equation we have already taken all the terms to the left. So no, whatever we substitute no the approximate solution here, and left side whatever we have, it will not be of course 0, it would be in terms of unknown constant A2. So whatever we get, we call that as a domain residual. So in this case we obtain the domain residual. So first is of course the du by dx. If you look at, in the approximate solution, so that is going to be a2 into 2x minus 2l, as you see from this. And then if you differentiate it twice, d2u by dx square would be equal to 2a2, because no, this is constant. So after differentiation, this is what you get. So then the domain residual usually we denote this by RD. R for the residual and subscript D for the domain is equal to, in the approximate solution, in the differential equation we are going to substitute this. So the differential equation, we have already said, EA into D2U by dx square, and D2U by dx square is 2A2, so we get EA and 2, let me write here A2, and the second term is Q. So we have taken all the terms in the differential equation towards the left, and in that we have substituted the approximate solution. Whatever we get, we call that as domain residual RD. So yeah, that is the third step, that is substitute the resulting after eliminating some of the unknown constants using boundary condition. Whatever solution we get, we substitute that in the differential equation and get this domain residual. Of course it is important that for, yeah, even the differential equation, given differential equation may have some terms on the left side, some terms may be written on the right hand side. So you'll have to take all the terms towards left, and in that you substitute the approximate solution. Whatever you get, that is referred to as domain residual. And then the last step is to obtain. Now the only unknown constant left out is actually A2. Our approximate solution is in terms of A2, and unless we get A2, we don't have final result, the final solution. So we need to obtain that. So the last step is that no, we obtain the remaining constants by minimizing the domain residual. So minimize RD. Now this minimization can mean actually many things. So we are going to discuss that what are the different ways we can actually achieve our target. So if there are a class of methods called the weighted residual methods. So those are I'm going to discuss. But before I actually go into this, for this particular problem, if you look at, we can easily say that this RD is zero throughout. No, if we say that this RD is equal to 0 throughout, so then from that equation we will directly get A2. So basically we can say that no, for in this particular case, in this case we can make RD 0, equate RD to RD equate RD to 0. So yeah, so now we do this RD equal to 0. So that is 2EA A2 plus Q equal to 0. So maybe for this problem, this step appears to be trivial. So from this, of course, you can get A2 equal to minus Q upon 2EA. So once you get this, so then you can say the solution is final solution, that is u is equal to, we had a2, so a2 is minus q upon 2ea and into x square minus 2lx. So this is the final solution of this problem. And now in this case, if you see, although no we followed the procedure of obtaining the approximate analytical solution, but no, we have exactly satisfied the boundary condition, because we got a0 and a1 in terms of a2. Of course, a0 is 0, so by exactly satisfying the boundary condition, and then we have substituted the resulting different no approximate solution in the differential equation, and whatever we get, we are equating it to 0. So that means no, the differential equation is also exactly satisfied. So for this problem, it actually happens to be exact solution, because now if you substitute this u in the differential equation, you will get left hand side equal to 0. That means left hand side and right hand side are same, so the differential equation is exactly satisfied, and therefore we get, through the approximate analytical solution approach, we got the exact solution of the problem. Of course, the exact solution, what you could have done is the, no, you have got this differential equation, so you integrate once, then integrate once again, and then you will get some, some function of x and constants, unknown constants c1 and c2, and then you will find out those constants c1 and c2, or whatever name you give to those constants, using these two boundary conditions. So if you follow that procedure, you will get actually the same solution. No, that's the approach to find the exact solution. But through this approach also, in this particular case, it is not no, it is not always necessary that we will get the exact solution which will exactly satisfy the boundary conditions and differential equation, but in this case we are able to get that. So we can say that since governing differential equation, since governing differential equation and boundary conditions are exactly satisfied, this is the exact solution. Of the given problem. Yeah, so now of course, if ea was a function of x, then you will not have the same situation. No, you'll have to do something different. Yeah, so are there any any questions, doubts, anybody? Yeah, so far whatever steps we discussed, are there any questions? Hello, am I audible?
Sir, you're audible.
Yes, sir.
Okay. Yeah. So yeah, if no, there are no questions, I think it is important that no, you ask. No, if you don't understand anything, then also you tell me. So, but no, you should
Sir,
make sure that, yeah, yes, please.
that for minimizing the domain residual,
Yeah.
like every time you have to equate to zero, or is
No,
there any other
no,
way?
no, no. In this, yeah. So I'm going to discuss what are the different ways that minimization concept we are going to implement. So in this case, we were able to do that. So in general, it may not be possible to do this. So I'm going to discuss that. Yes. So minimization could mean actually no, because this domain residual could be function of x, so it could be positive or negative over the entire domain. So we take its square and then integrate and then minimize that. So that is one possibility. We call that as method of least squares. So I will be discussing that. And in general, what we call as weighted integral or weighted residual method. So that is what we will be actually doing that. So somewhat similar to equating it to zero, but not directly, but no, indirectly. So now let me take another example. So say example 2. Now the in this case I'm going to take, say, a beam problem. So beam problem means Euler-Bernoulli beam, and let us say that the beam is simply supported. So one side it is no, on a hinge support, other side on a roller support. This is the beam, and the length of, so cross sectional dimensions are much smaller compared to the length. So that is what you call beam. And no, this is your x-axis and this is y-axis. Along y direction we measure the transverse displacement in this case. So the unknown variable in this case I'm going to take as the transverse displacement. So this q is the force per unit length, but in the earlier case the load was along the x direction, along the length of the rod. In this case load, the q is perpendicular to the rod. No, so that is load, and L is length, and also we need another quantity called flexural rigidity. So that's the product of no, Young's modulus and second moment of area I about z axis. So this is actually izz. I am writing ei. So for the time being, let us say that we know the differential equation. So I'm not deriving the differential equation for this case. At some point of time, we will derive that when I discuss finite elements. But for the timing, I know we want to apply the method of weighted residue. I know this approximate analytical solution to solve this problem. So I'm going to assume that no, we know the differential equation. So for this problem, the governing differential equation is, and this governing differential equation is based on Euler-Bernoulli beam assumption. So governing differential equation. So that is basically Ei and d power 4v by dx power 4 minus q equal to 0. So in this I am assuming that Ei and q they are constant along x. Otherwise, this differential equation would have been d2 by dx square, then a whole ei into d2b by dx square. So since ei is constant, so it is taken out of the differentiation, so you get this equation. So this is the based on Euler-Bernoulli beam assumption. That is the one aspect you'll have to keep in mind. So valid for thin beams. That means the cross-sectional dimensions are much smaller compared to the length. And the boundary conditions. So one boundary condition is that now if you look at it is hinged. So both left and the right end. So if you look at the left end at x equal to 0, v will be 0 because no, it is pinned, so this point cannot move. So v would be equal to 0, and similarly the right side also it would be 0. So v equal to 0 at x equal to 0 as well as at x is equal to 12. So am I writing I am writing that as v equal to 0 at x equal to 0 comma l. And the second set, this is a set, that is these are actually two conditions: v equal to 0 at left end, v equal to 0 at right end. And then another set is actually no, for the spin support the bending moment would be 0 because the support is such that no, it allows the rotation of the beam about this point by about z axis passing through the left point, z axis passing to the right side. So bending moment in that case would be 0. And in Euler-Bernoulli beam theory, bending moment is actually ei into d2b by dx square. So that is equal to 0. So we can say ei, we can divide both sides, and then finally we get basically d2v by dx square equal to 0 at x equal to 0 comma l at both the ends. No, the same situation, because both the ends the support allows free rotation of the beam, so then the bending moment has to be 0 over there. And so these are the four boundary conditions, to these and to these boundary conditions. And now in this case, I'm going to know, although one possibility is that we again start with a the first step we can start with an approximate solution taking v. Now in this case, now we want to take a polynomial. So if you want to take a polynomial, then whatever we take, that should be differentiable at least four times. So if you want to assume an approximate solution which is differentiable four times, so it should have terms like at least up to x power 4. So the solution would be like a0 plus a1x plus a2x square plus a3x cube plus a4 x power 4. So that's the minimum. Of course, I think yeah. So I forgot to tell you one thing over here, that once you have got this solution, so you can differentiate this, you get the strain as a function of x. You can calculate the strain epsilon xx, which is du by dx at any point, and then stress, which is e into du by dx. So from this solution you can get the stress at any point. Of course the maximum stress would be at the left end. So those also you will be able to do once you get an approximate solution. So you should be able to calculate the strain, then you should be able to calculate stress, and no, so those would be of interest in designing this member. So yeah, coming back to this, so I was saying this is what the minimum solution you have to assume, x power 4, so that it is differentiable four times. And then the next step is that we eliminate some of the constant by satisfying the boundary conditions. So the next set of steps we will do that v equal to 0 at x equal to 0. So that means when we put x equal to 0 in this, all the terms will be 0, only a naught will be there. So this will give us a naught equal to 0. Then the second condition is that v equal to 0 at x is equal to l, and that will give you basically, if you first differentiate this with respect to x, no sorry, no not the derivative, but the v itself. So a naught is already 0, so we get a1l plus a2l square plus a3l cube plus a power 4 a4 into l power 4 equal to 0. So that's the second thing. Then third is d2v by dx square equal to 0 at x equal to 0. So from this, now if you differentiate the approximate solution twice, so let me write the expression for d2v by dx square. So this any will go in the first derivative itself, this will go in the second derivative. So the second derivative of this term would be 2a2, and the second derivative of this will be 6a3x, and the second derivative of this will be 12a4 x square. So that is the second derivative which is going to be there. So now if you put that x equal to 0 in this, you basically get 2a2 equal to 0, and that gives you a2 equal to 0. And so a2 is also 0. And then the other condition is that d2v by dx square is equal to 0 at x is equal to l. These are the four boundary conditions, 1 2 3, and there's the fourth one. So now from this you will be able to get, now we put x is equal to l in the expression for d2v by dx square. From this we already said a2 equal to 0, so we will have only these two terms. So we will have 6a3l plus 12a4l square equal to 0. So now what you can do is, in this equation, if you look at now this particular equation, you can put a2 equal to 0. So this equation is yeah, we have in terms of a1 a3 and a4. No, it would be in terms of a1 a3 and a4. This equation is also in terms of a3 and a4. So what you can actually do, using this equation and this equation, these two equation, you can express a3 and a4 in terms of a1, and then you will get the approximate solution v, which is will be in terms of unknown constant a1, and of course the function of x. And then you substitute that in the differential equation, get the domain residual, and then kind of similar kind of a minimization, you can get the constant a1, and therefore finally you have the approximate solution. And once you got v, you can calculate the the axial displacement, which would be minus y into dv by dx. At any point you can calculate strain epsilon xx as minus y into d2v by dx square, and the stress e into y minus e into y into d2v by dx square, you can calculate at any point. So those are the steps. So I think I give you as a home assignment, so please complete this problem. It is exactly the way the first problem is done. Only thing is that you have to solve these two simultaneous equations to express a3 and a4 in terms of a1, and then follow the same steps which we did for the first example and solve this problem. Now let me in this case, let me think give you another example. Let us say that we assume no, rather than a polynomial, although once you get the no get no express a3 and a4 in terms of a1, and then domain residual, and then find out a1 by equating domain residual to 0, whatever solution is you will, that is going to be actually an exact solution of this problem again. So through the approximate analytical solution approach, you would be able to get the exact solution. But let us say that no, we want to assume v equal to, rather than polynomial, I just want to take this a1 into sine of pi x by l. Let us no, rather than polynomial, let us assume a trigonometric function, and only one term trigonometric function. So sine, that is a1 into sine pi x by l. A1 is a unknown constant, and this is sine pi x by l is a function of x, as you know this case. So now if you look at the boundary conditions, so this expression, if we put x equal to 0, you will get v equal to 0. If we put x is equal to l in this approximate solution, again it would be a1 sine pi would be 0. So you will get v equal to 0 at x is equal to l also. So that means the first set of boundary conditions will be automatically satisfied by this. And now if you look at the second set of boundary conditions, so if you differentiate this twice, so you will get d2v by dx square is equal to, when you differentiate it twice, minus a1 pi square by l square again into sine of pi x by l. That's the second derivative. And second set of boundary conditions is that d2v by dx square at x equal to 0 and x is equal to l. So again, if you put here x equal to 0, sine 0 is 0, so d2v by dx square is 0 at x equal to 0. If you also put x is equal to l, again you will get d2v by dx square equal to 0. So you can see that if we assume this as an approximate solution, all the boundary conditions are actually satisfied. So no, we have finally, that means the solution which is in terms of unknown constant a1 satisfying all the boundary conditions. So sometimes you can make a guess and assume a solution, approximate solution, which already satisfies the boundary condition. If it doesn't, then of course you have to eliminate some of the constants by satisfying the boundary conditions. So in this case, you see that all boundary conditions are satisfied. So if all the boundary conditions are satisfied, then what you do is now substitute the solution in the approximate differential equation and get what is known as the domain residual. So now similarly, if you in the differential equation we have highest derivative as fourth derivative, so d power 4 upon dx power 4. So if you differentiate this 4 times, you will get plus a1 pi power 4 upon l power 4 again into sine pi x by l. So this is what will be the fourth derivative, and therefore the third step, domain residual rd, will be ei into d2 v d power 4 a v by dx power 4. So that will become ei into a1 pi power 4 upon l power 4 into sine of pi x by l minus q. So this is going to be the approximate no the domain residual. And now in this case, now you think over how do we know find out this unknown constant a1. So now can you tell me some ideas how can we find now a1 in this case? Of course, our aim is to minimize this rd. So that means over the entire domain from x equal to 0 to l, this should be as low as possible. No, the magnitude of rd must be as low as possible. So that's the goal in finding out the approximate solution. So can some of you tell me what your ideas? How can we do that? How can we minimize this? Now you see in this case rd is a function of x, so that is what you see here. So can you please tell me how some of your ideas how we can now find constant a1 by minimizing this rd domain residual? Yes, please. I think I expect some answers from your side. Whatever, no? Yes.
Minimize the value of sin x that is 0.
Yeah, please say again. I think your voice was not clear.
So we can minimize the value of sin x that is 0 to 0.
We can make sine pi x by l 0.
Sin pi x by l is 0, sir.
Okay, you are
Then
saying that we take sine pi x by l equal to 0. I think that will not make this RD will be no, if sine pi x by l is 0. So it cannot be, no, it can be 0 at x is equal to 0 and x is equal to l. But in between 0 to l, see this sine pi x by l is not going to be 0. So that is not yeah, that is not possible. But maybe some of you might think that we can equate this residual to 0, let us say. As such, if we say it is equal to 0, some thought process you may have, and then express a1 is equal to q divided by this ei pi power 4 l power 4 sine pi x by l. So you will have to keep in mind that a1 is a constant. It cannot be a function of x, so we cannot do that. In this case, it is not possible to make the residual 0 everywhere in the domain. Absolutely we cannot. In the the earlier two cases, the first example, in the second example, the first approach, it was possible to make the domain residual 0 everywhere, but in this case it is not possible. It's a function of x, and if we equate it to 0, we get a1 as a function of x, which is contradictory because a1 is a constant. It cannot be function of x, so we cannot do that. So now for actually finding out these constants, what we call in the approximate analytical solution methods, we call a method called weighted residual statement or weighted integral statement. So we use that. So that next topic I'm going to introduce is the weighted residual statement. And what is the need? Because now in this case there is only one constant. Sometimes we may have the solution which has got, after satisfying the boundary condition, we may have more number of constants. So depending on how many left out constants are there, we need that many equations to solve for all the unknowns. So to generate the number of equations equal to the number of unknown constants, we use a method which is known as weighted residual statement or weighted integral statement. So now for in the earlier two cases, the first example and second example, first case, we could solve that problem using this weighted residual, and we will get the same solution actually. So weighted residual statement are sometimes we also call that as weighted integral statement. So as this name suggests, one, it is saying residual is coming, weighted is coming. So that our residual we have already defined, it is the domain residual RD, and weighted means we kind of multiply some weight function, and then no, we want it to be independent of x, so we integrate it over over the domain, so in this case over the length. So the weighted residual statement is written as integral 0 to L, or the integral over the entire domain of interest, for which we want to solve the problem. So W into RD dx equal to 0. So in this, what we have done, we have this domain residual RD, we have multiplied by the weight function W. In general, RD would be function of x, W is also function of x, but known function of x. W is a weight function and it is a known function of x. We integrate this and equate it to 0, and we choose the number of weight functions W equal to number of unknown constants, so that we get number of equations equal to the number of unknown constants. So RD, you already know, it is the domain residual, and W is the additional term which I have introduced. So this is known as weight function, and can be chosen equal to the number of unknown constants. Can and should be chosen, and is a weight function, and number of weight functions will be or should be equal to number of unknown constants after satisfying the boundary condition. So this is very important statement, that is integral 0 to L W RD dx equal to 0. In this process, we of course, in specific cases you might get this process might lead to RD equal to 0 everywhere, but in general it will not give, but in some weighted average sense, that residual we are making it equal to 0. So now if you want to apply this, so now how do we, depending on how we choose W, what we choose as W, we have different weighted residual methods called Galerkin method, Petro-Galerkin method, method of least squares, collocation method. So these are the four, or you can have subdomain collocation. So you can say there are 5 weighted residual methods which are used for solving the for finding out the approximate analytical solutions, and these methods are also used to develop the element level governing equation in any problem which we want to solve using finite element method. So now let me discuss how do we choose. So I will go with this example itself, the with the approximate solution as a1 sin pi x by L. So now for the given problem, we already have said that domain residual RD is EI pi power 4 upon L power 4 into A1 into sine of pi x by L minus Q. So this is the domain residual. And now, as I already said, depending on the choice of W, different weighted residual methods are there. See, depending upon the choice of W, that is a weight function, different weighted residual methods are there. Different weighted residual methods are there. So first one is Galerkin method. So let me discuss one by one. The first one, Galerkin method. And of course, no, there is no derivation for these. No, you cannot derive these methods. So this is a statement, and it is what actually, if you want to interpret this statement. So for solid mechanics problems, structural mechanics problems, this RD is basically going to be the residual force, and weight function is actually kind of what we call as the variation of displacement. So ultimately, by doing this, what we are doing is we are doing the virtual, equating virtual work to zero. So this statement is amounting to equating the virtual work, because no, whether you look at EA into d2u by dx square plus q as a residual, or you look at this EID power 4 by dx power 4 minus q. So these are the unbalanced forces essentially. And when you multiply w, it's kind of no virtual displacement, and when you integrate and no do this, you what you get is the virtual work. So in a way, we that's a basically kind of generalized principle of virtual work. So you can also interpret it like this. So now, no, depending on how we choose the weight function w, we have different methods. No, so first one is Galerkin method. So in this case, in case of Galerkin method, the weight function w, how do we choose w is, in now we have approximate solution. After satisfying the boundary condition, yeah, now you got approximate solution which is satisfying the boundary condition, and it will be in terms of some unknown constants. So if we take the coefficients of unknown constants in the approximate solution as weight functions, then that is known as the Galerkin method. So in this method, weight function is the coefficient of weight functions are the coefficients of, or you can say weight functions are chosen, whatever you say, weight functions are, or the weight functions are chosen as the coefficients of unknown constants, unknown constants in the approximate solution. So now the problem we are taking, so we said v equal to a1 into sine of pi x by l. This already satisfies the boundary condition, so you can say that is this is the assumed solution which satisfies the boundary condition. So in Galerkin method, we would choose w as the coefficient of unknown constant. So here a1 is unknown constant, its coefficient is sine pi x by l. So the weight function w is chosen as sine pi x by l. So this is basically chosen as the weight function. Now suppose, yeah, so I'm going to work out this no the example, but let me in the Galerkin method, what if we would have solved the first problem? So let me go to the first problem. Suppose no, in the first problem we had got this as the domain residual, as you know, and the approximate solution will be no, this is the approximate solution after satisfying the boundary condition, as you see here. And in this, the unknown constant is a2, and no, its coefficient is x square minus 2lx. So if you wanted to find out a2 using Galerkin method, then you will choose no, the weight function w as x square minus 2lx, and then take integral 0 to l w rd equal to 0. Your rd is of course this, and you will find that of course for that problem, no, this problem will get same a2 what we have got here by equating it to 0 everywhere. So but I wanted to emphasize that in this case, in Galerkin method, the weight function w would be x square minus 2lx, because that is the coefficient of unknown constant in the approximate solution after satisfying the boundary condition. Similarly, in the this problem, if you are if we are to take the, no, I have given you this as a assigned no, homework problem. So whatever I say, of course you must do. Those are important things which I leave for you to do. So in this, after eliminating a3 and a4, you will get the approximate solution in terms of unknown constant a1. So the weight function will be that coefficient of a1 and this. And for this, where we have assumed the approximate solution as a1 sine pi x by l, the weight function w is sine pi x by l, which is the coefficient of a1. So it's very important that you first your approximate solution should satisfy the boundary condition, or you eliminate some of the constants by satisfying the boundary condition, and then if no whatever is the unknown constants, their coefficients are your weight function. Now in this case, because there is only one unknown constant, so only one weight function. If there are more unknown constants in the approximate solution, you will get more number of weight functions. Then how do we find A1? Is through the weighted residual statement, a weighted integral statement. So now we have integral 0 to L. The weighted residual statement is WRD dx equal to 0. So now integral 0 to L, W is already, I have said, sine pi x by L, and domain residual is EI pi power 4 upon L power 4 A1 sine of pi x by L minus q. This is your domain residual. Dx, the integration has to be done over the domain. So in this case, over the entire length. And now if you carry out the integration, so the first term is going to be sine square pi x by L. Its integral from 0 to L would be actually L by 2. So you will get this as pi power 4 upon L power EI, of course, pi power 4 upon L power 4 into L by 2 into A1. That's the first integral. And no, the second term is no, you have to take this sine pi x by L inside and then integrate each term. So there are two terms here. I hope you can do this integration, right? So because I am writing the result directly. If any one of you have difficulty, then let me know. I can expand sine square pi x by L in terms of cos 2 pi x by L and show you how the integral is done. So I'm assuming that you know this integral. If you don't, please let me know. So the integral of the first term sine pi square sine square pi x by L is L by 2, and other terms are the ci pi power 4 L power 4 A1. They are already there. The second term is going to be integral 0 to L minus q into sine pi x by L. The integral of sine pi x by L 0 to L is going to be basically 2L by pi. So that will become minus 2QL upon pi, and this is equal to 0. Now we are equating this weighted residual by integral of the weighted residual equal to 0. So from this we will be able to find out basically the constant A1. So you would see that A1 would be equal to, if you simplify this, so your A1 is going to be 4QL power 4 upon EI pi power 5. So that is what we get as the solution A1 now using this. So you can say that now once you have got the A1, so you can say the final solution is V equal to A1, which is 4QL power 4 upon EI pi power 5 into sine of pi x by L. So this is the solution. Suppose now we are interested in a slope to calculate at any point using this approximate solution. Obviously, this is not going to be exact solution. Now, if you substitute this in the approximate in the differential equation, so you will find that the residual is not going to be zero everywhere, but its weighted integral is zero. So rather than making the residual, it is, see, in general for complex problems where properties are functions of x, ei is a function of x, q is a variable, and so on, and depending on, of course, what kind of approximate solution you assume, it may not be possible to make residual zero everywhere, but we can make its weighted integral zero. So that is what we are doing. And depending on how you assume the approximate solution, sometimes these can also give the exact solution. So as special cases, B may get a residual equal to 0 everywhere through this route. But now in this case, you see, we have assumed this sine pi x by L as the solution. So B will not be getting the residual 0 everywhere, but we will get this. Now, of course, you have got V, then you can calculate its slope. So you will get dV by dx. dV by dx will be 4Q L cube upon EI pi power 4 into cos of pi x by L. And now the second derivative you want to get, dB by dx square will be equal to, so minus, you will get 4Q L square upon EI pi cube into sine of pi x by L. So once you have got these, so basically I have not explained you all the the relations for Euler-Bernoulli beam, but no, at any point in the beam, if you want to find V is the transverse displacement, I know this is the beam, and I already said this is x coordinate and this is y coordinate. At any point at a distance y from x axis, if you want to find the axial displacement, so u would be equal to minus y into dv by dx. So what is done in this, that this is the beam in the undeformed configuration. When this beam bends, so it may take some shape like this. So this normal which is here remains normal to the deformed center line, but it rotates. So this is the rotation. Now this from the center point, if you take any point at a top side, this one, so this distance is y into this angle is dv by dx. So y into dv by dx is this displacement. So you but it is along the negative x direction, so this is the axial displacement. Although this I will actually explain you in more detail when I talk of finite limits. So this is axial displacement, and then when you want to get the strain, so epsilon xx, in this case the non-zero strain is independent strain is going to be epsilon xx, which is the derivative of u du by dx. So that is du by dx, and du by dx in this case minus y into d2v by dx square. So as you see, the strain is going to vary linearly as a function of y. So you already know this d2v by dx square, so you can calculate this at any point. So of course the as you know, the maximum strain and stress is going to be at center, so you can calculate d2v by dx square at x is equal to l by 2 and find out what is the strain. And then of course the stress sigma xx would be you can find out E into du by dx, that is strain, epsilon xx, so that would be minus E into y into d2v by dx square. Why I am telling you this, because ultimately you would be interested in finding out the stress for design purpose. You'll have to either find out some of the cross-sectional properties, so that maximum stress does not exceed the design stress based on either real stress or ultimate stress, or sometimes strain. So you also need to calculate these quantities. So yeah, so the first thing we did here is this Galerkin method. That is one of the weighted residual method known as the Galerkin method. For the approximate solution is chosen as the coefficient of no, sorry, the weight function is chosen as the coefficient of unknown constants in the approximate solution. So that's not the only method, although no, if you say that why do I worry about other methods, I can just work with the Galerkin method, that is also fine. But there are other methods people have proposed, so I know at least we should know, although we may most of the time we might actually use Galerkin method or the equivalent this Rayleigh method, which I will be discussing subsequently. But we should know those other methods. So now the second method under the weighted residual methods is known as Petro-Galerkin method. And names of these methods are known by either Galerkin or Petro-Galerkin is because they are the person who proposed it for the first time. So Petro-Galerkin method. Now in this case, as I already told you, the different methods are how we choose the weight function. So in this case, the weight function is chosen uh, something different from what is there in the what is there as a coefficient of unknown constants in the approximate solution. So that's the main thing. So we say that weight functions in this method, weight functions are different from the coefficients of unknown constants in the approximate solution. So now for the given, so you understand, no, we have unknown, the approximate solution in this particular case, a1 sine pi x by l. So the coefficient of a1 is sine pi x by l. So anything different from that, what we choose, no, then the resulting no method is Petro-Galerkin method. So for example, I can simply choose say w equal to 1, I can choose w equal to x, I can do any one of these things. So let us say w equal to 1, and it is different from the sine pi x by l, so different from the coefficient of unknown constant in the approximate solution. So therefore this is known as the basically Petro-Galerkin method. So main difference is that a weight function is different from the coefficient of unknown constants in the approximate solution. So now we want to use Petro-Galerkin method and find out the constant a1. So then we again use this integral 0 to L w rd dx equal to 0. So integral 0 to L w is 1 now, and your rd is you see this is ei pi power 4 upon L power 4 into a1 into sine of pi x by L minus q dx equal to 0. So now if you see, and know if you want compare the different predictions, you can actually evaluate say w at the v at the center, not w, v, that is transverse displacement deflection at the center, using these different methods, and see how accurately they are predicting. And the based on the polynomial solution, what you will actually get is the, you can say for this case, exact solutions. So you can compare how these solutions compare with the the exact solution. So now in this case, w I have chosen as 1, I could have chosen w as x, I could have chosen w as x square, anything. W equal to 1 simplifies the integration, so I am using that. But whatever I do now is, we can say that we have solved the constant a1 from the Petro-Galerkin method. So now if you do this integration, so this is already unity, so the first integral is basically ei pi power 4 upon L power 4 into a1, and the integral sine pi x by L will be 2L upon pi. We have already done that. And the second integral is simply q in integral dx, that would be q into L, and is equal to 0. So now if you look at this, so you will find a1 would be equal to q L power 4 upon twice of ei pi q. So this is what you get as your a1, and therefore finally you can say v, the approximate solution, is q L power 4 upon 2 ei pi cube sine of pi x by. So only the coefficient is changing, of course the other things remain same. So this is known as the Petro-Galerkin method. So main difference is that we choose the weight function different from coefficients of unknown constants. In this case we have taken w equal to 1, and therefore it is different from coefficient of a1 in the approximate solution, that is sine pi x by L, and therefore this is Petro-Galerkin method. The third is known as the method of least squares. Third, no, the Betted integral method is known as the method of least squares. So as the name suggests, B basically something, we have to square the residual, integrate it over the entire domain. So square means we square the residual here, and then we integrate it over the entire domain, and whatever we get, we minimize that. So in this case we are doing the minimization, the baby said that we need to minimize the residual, although also in this case what we do is minimize the integral of is minimize integral of the square of residual. So that is what we do. So for this case what we will do is now the problem at hand. Now when you do the integral, so let me write first. So integration 0 to L and b square rd, so it would be rd square. So first b square integrated over the entire domain. So because when you do the integration, x would be eliminated, x would have gone out, and then rd would be another function of unknown constants. Now in this case would be function of a1. So we minimize this with respect to I. So maybe basically minimize with minimize this with respect to a1. So I will say minimize I with respect to a1, where I is 0 to L rd square dx. So minimize I with respect to a1, and where I is integral 0 to L rd square dx. So we are squaring the residual, then integrating it. The resulting expression is going to be function of unknown constants. And now then we minimize this by, so we use the first order necessary condition for the minimization. So I think you would have studied maxima and minimum in your basic mathematics courses. So if you have any function f which is a function of x, the first order necessary condition for its minimum minima or maximum is that df by dx equal to 0. So we do the same thing here. So now if there are more number of constants, these will be partial derivative, because in this case if you look at rd, we have already seen the rd. If you look at the expression for rd is this is rd, so function of only constant a1. We square it and then integrate with respect to x. Finally it would be function of a1. So we are minimizing this integral rd square dx with respect to a1. So we will get basically del I by del a1. Actually no, in this case it's a total derivative equal to 0. So now if you do that, so what we can do is we are minimizing with respect to a1, and integral is with respect to x. So we can take the differentiation sign inside the integral. So we will get integral 0 to L, and then now we want to differentiate now this with respect to a1. So first we differentiate this rd square with respect to rd, so that will give you 2rd, and then the derivative of rd with respect to x, so that will give you drd by da1 dx equal to 0. So now what you can actually do is this 2 you can divide both and left side and right side. So finally you can say this is 0 to L, and then we have I can first let me write the second term. So that is drd by da1 and into rd dx equal to 0. So now if you look at here, now we want to compare with the weighted residual statement. So the weighted residual statement was WRD dx equal to 0. So you will see in this case, therefore we can say that W is nothing but DRD by DA1. So you can say in the method of least squares, the weight function is derivative of domain residual with respect to unknown constant. So you can say in the method of least squares, weight function is weight function is a derivative of residual domain residual with respect to unknown constant. So this is known as method of least square, where the weight functions are chosen as the derivatives of domain residual with respect to unknown constants. In this case, there is only one unknown constant a1, so only one weight function. And if there are more number of unknown constants, so then rd would be function of that many number of unknown constants, and then they will have number of weight functions. It would be partial derivative of domain residual with respect to those unknown constants. So now we want to solve the problem. Now for the given problem, so we have already said that no rd is EI pi power 4 upon L power 4 into A1 into sine pi x by L minus Q. So if you look at dRd by dA1, so you will get basically EI pi power 4 upon L power 4 into sine of pi x by L. See, we are differentiating with respect to A1, so this is the term which has A1. And now of course this is just a constant, so you can finally say that in this case W is going to be simply sine pi x by L, because we can divide. No, this is a scaling factor in the whole equation, this will be there, so we can divide it by that. So W is equal to sine pi x by L. And now in this particular problem, the interesting thing you would note that now this is in this, only in this particular case, it is not always necessary, but only for this particular case you see that no, the W is equal to sine pi x by L, which is same as what we had in the Galerkin method, not the Petro-Galerkin but Galerkin method. So we had as W equal to sine pi x by L. So you will see the solution is going to be same as Galerkin method, because weight function is same, so the constant A1 is going to be same. And this is only for this case, but in general the solution from the method of least squares would be different from what we get from the Galerkin method. So now so let me just state that. So in this case solution is same as Galerkin method, because weight function is same. Solution is same as Galerkin method. So now we talked about Galerkin method, we talked about Petro-Galerkin method, we talked about method of least squares. So the last thing is no, the natural way to think is that when we have residual, domain residual as a function of x, we can at selected point we actually equate that residual to 0, and the resulting method is known as point collocation method. So the fourth method I am going to discuss is that is known as point collocation method. Point collocation method. So in this case, rather than not taking the integral at selected points, we equate the residual to 0, and from the resulting equations we solve for the unknown constants and then get the approximate solution. So in this method what is done is point collocation method, the residual set residual equal to 0. Set means basically equate set residual equal to 0 at selected points. Selected points, these points are known as collocation points in the domain. And number of collocation points would be equal to number of unknown constants in the approximate solution, after of course satisfying the boundary condition. So number of collocation points equal to number of unknown constants in the approximate solution after satisfying the boundary condition. So now for the problem at hand, we have only one the unknown constant in the approximate solution, that is a1. So we need to choose only one collocation point. So this is the domain, and we can choose any point. Let's say center, we want to make the residual equal to 0 at the center. Of course, no, it will be then that means we are giving more importance to the center point. So that means at center the residual would become 0, but at other location it may be actually more. So that means, from 0 to L by 2, and from L by 2 to L, the residual may be more, of course, in the process. So we just want to choose this as a residual, no, the collocation point. So let me call that as x1. So x1 is equal to L by 2 is the collocation point. Because we need only one collocation point, we can choose anywhere. I am choosing center, and so we get this, and therefore from this we will say that rd, which is a function of x, is 0 at L by 2 equal to 0. This is no, rd evaluated at L by 2. That is what it means when I write it like this. This is not rd into L by 2. So we know rd is, now if you look at the rd, we already know that, no, this is rd. RD we have, yeah, what I it's written over here. So this is your RD, and if I evaluate it at x is equal to L by 2, so this term is, no, you will get sine pi by 2. X is equal to L by 2, so sine pi by 2, pi by 2 is unity. So you get this as basically EI pi power 4 upon a power 4 into a1 minus q equal to 0. So this will give you a1 is equal to ql power 4 upon ei pi power 4. So yeah, this is known as the collocation method. So as I already said, you can calculate value of v at L by 2 using these different methods, and then you can see how they compare with the approximate analytical solution. Of course, as a method, when we use, we'll have to actually take the sufficient number of terms, and if we take sufficient number of terms in the approximate solution, the all methods are expected to give you the kind of accuracy you need in the solution. So you can, by taking more and more terms in the approximate solution, you can get the solution of desired accuracy. So finally, solution v will be equal to, in this case, ql power 4 upon ei pi power 4 into sine of pi x by L. That's the solution in this. They're using this method. So I think, yeah, the last thing is to discuss is the subdomain collocation method. So I think it's already 10:50. So no, I want to stop here, and you can ask any doubts and questions you may have. So in the next class, I will discuss the subdomain collocation, and then one another important thing as part of this better residual method is actually weak form. So I will introduce the what we mean by strong form, and then what is weak form, and how do we obtain that, and what additional information we get from that, and then how do we obtain the integral functional, which is kind of a total potential energy functional, and how we solve problems using weak form. So those are the things I will be discussing in the next class. So now any questions and doubts? Yes. You know whatever we discussed, any question, any doubt, you have not understood anything, please ask. Yes, anybody, any question, doubt, anything? No, if you have not understood anything, then also you ask, but I think I expect some questions.
Excuse me, sir.
Yeah.
Sir, instead of this sine function, if we had taken the polynomial,
Yeah.
then how accurate this answer will be, like using Galerkin and Petro-Galerkin?
Actually, if you just have taken the polynomial, in this case, whether you use the, for this particular example, if it was a polynomial with terms up to x power 4, both Galerkin as well as Petro-Galerkin methods will give you the same solution, in fact, in this particular example. and in general you cannot say that which is more accurate, but the use of Galerkin method is more common, because it is obvious the once the moment you have your assumed approximate solution after satisfying the boundary condition, so it is easy to know what are the weight functions w. Most common method is actually Galerkin method, because weight functions are easily identified. So we use that. But accuracy wise, if you see, it actually depends on the problem to problem and what form of the approximate solution is chosen. But for this problem, they both will give the same. Now, if you assume the solution as a polynomial, both problems are going to give you same solution.
Yes, sir.
Uh,
Yes, sir.
I have a class. Yeah. Yes. Anybody else? Any other question? And now see, let me kind of give you some graphical. So if there are questions, please ask. Now what we are actually doing is, why we use these methods is, say, after satisfying the boundary condition, we got the approximate solution and then the residual. So in general, along the length, see, this is your x coordinate, and then if you plot your RD, so RD could be some function of no x, could be throughout the domain, could be positive, could be negative, could be changing from positive to negative, so it can have any variation. Now what we are doing is, in case of collocation method, we are equating the residual to zero at selected points. So if you equating the residual to zero over here, so then you are making it zero over here, but then other places it may actually increase. In case of Galerkin or Petro-Galerkin method, what you are doing is, you are choosing the weight function, and that you are multiplying the weight function. So now the weight function has got more value at closer to x equal to 0, then you are minimizing, making the residual closer to 0 near x equal to 0. If the weight function is more towards the another center, then you are making residual close to 0, more close to 0 at center. And if it is the value of weight function is more towards x is equal to L, then you are making the residual more close to 0 towards x is equal to L. So essentially you are trying to kind of putting some weight onto this weight function, and then bringing it closer to the 0. So that is what this weighted residual integral statement, or weighted residual statement actually means. That we have some residual, we put some weight, so we, by putting that weight, we are trying to bring it closer to 0. And in collocation, of course, at a one particular point you are exactly making it 0, but in the process at other points it might actually increase. So if you have more number of collocation points, it will be 0 at those more all the collocation points, but other places it may be more. Of course, when you keep on increasing the collocation points, you will find that most of the places the residual would be closer to 0, and that means we would be more close to exact solution if we have more number of collocation point, and that means more number of terms in the approximate solution. Yeah. Any question? Anybody? So if there are no questions, I'm stopping here. Thank you all for your attention. Yeah. Thank you very much. Please go through whatever I'm discussing, and also ask questions and doubts. So that is what I expect. Okay. Thank you all for your attention. Thank you. I'm stopping.
Thank you, sir.